Hello everyone. Let's resume our class on pile foundation. This time we are going to talk about Meyerhof method for estimation of the end bearing capacity of pile. Okay, so we are not talking about the shaft capacity, shaft friction yet. This one is only for the pile tip, the end bearing capacity. Okay, so there are several methods. Now this one is the first one we will attack. Previously, we have already discussed this general equation, this general formula, okay? And this is the equation we learn for the pile tip, for the end bearing capacity, and this one is for the shaft capacity. So there is a method developed by Meyerhof for estimation of the end bearing capacity in sand and in clay. Okay, only this one, the end bearing capacity. The shaft bearing capacity will come later. This is the beginning of a series of methods. Okay, so let's discuss this, the end bearing capacity in sand first. Okay, so this is the general equation. So what do we expect? As you know, in sand, there is no cohesion. So you can already guess what will the equation become. Okay, so once again we are looking for this tip, the end bearing capacity. Okay, so when we look at this equation of end bearing capacity, you can see the effective stress at the level of the pile tip, this level. Okay, so what do we expect if the embedment of the pile increases? Normally, when the embedment increases, the the effective stress also increase, right? Because it just overburden pressure normally. But many experiences, many study show that when the embedment increases, the end bearing capacity will increase, the point bearing capacity will increase until a certain depth is reached. Okay. Once that depth that we will call here critical depth is reached, then the end bearing capacity will reach a maximum value and remain constant. Okay, so instead of talking about depth here, we will talk about embedment ratio. Okay, ratio of embedment, that is the embedment length of the pi LB that divided by the pile diameter or the pile width. So LB divided by D. Okay, this ratio, when the ratio increase, the bearing capacity, the end bearing capacity will increase until you reach a certain ratio, that is here critical ratio, from which the end bearing capacity doesn't increase anymore. There is illustration of this here. This figure 14 is showing us. You can see here, this is the horizontal axis is for the tip capacity, the end bearing capacity, and this is depth. Okay, the ratio L divided by D, this ratio. Okay, so you can see the bearing capacity, the end bearing capacity is increasing with depth. It increasing up to here, then it becomes almost constant. See, so at this depth, you can see these steps, is what we will call critical embedment ratio. The critical embedment ratio. Okay. In this case, L is equal to LB. Okay. LB has a definition. We will give it later. So I will put this here. Okay. When the embedment ratio reaches a critical one, then the end bearing capacity will become constant. But before that, before reaching this critical ratio, critical embedment ratio, the bearing capacity, the end bearing capacity increases with depth, with increasing depth. Okay, so in uniform ground, okay, if the soil is made, ground is uniform soil, then this L is equal to LB. It means what? It means the embedment, the total embedment of the pile is taken as LB. Okay. This LB, be careful, it doesn't mean the total, it doesn't mean the embedment of the pile in all cases, except in the case of uniform ground. If you get homogeneous soil, then the actual embedment of the pile is also LB. Okay, then you take this LB, divide by the pile diameter to get this ratio. Okay, then if your pile is penetrating a hard like bearing stratum, for example, you can see here, this line is maybe, let's say the bearing stratum is here. But if the pile was a little bit penetrating into this bearing stratum, okay, then the LB will be less than the actual embedment than L. Okay, but this is like a very particular case that we will discuss later. Okay, right now we are dealing with uniform ground, homogeneous soil. Okay, so in that case, L, the pile embedment is equal to LB, or let's say LB is equal to the real pile embedment, and then you can do the ratio. Okay, but the critical ratio is when this the end bearing capacity becomes constant. So when the end bearing capacity becomes constant, the QP means the end bearing capacity is equal to QL. It means limit. It means the limit end bearing capacity, the maximum end bearing capacity. This is the limit QL. Okay. So no matter how deep you go, no matter how deep you go, how uh, how long your pile embedment is, there is a limit, Q limit. It doesn't like increase forever like this line. No, it has a limit. Okay, so remember about this limit. Now, beyond beyond the critical embedment ratio, as you know, I think this is what I just explained. The end bearing capacity remain constant. So we have QP equal QL. This is what is written here, and this is what I just explained. Okay, in this figure. So now we will come back on equations. Okay, what you need to understand here is just at the beginning, the end bearing capacity increases with the increasing depths until a certain depth, critical depth, and then it becomes constant, equal to this limit. That is, so critical embedment ratio, which is here, that ratio from which the end bearing capacity becomes constant. Okay, so about the equation now. This is the equation for the end bearing capacity of pi, the general equation. But if we are dealing with sand, then C cohesion is 0, right? So this part becomes 0. So it means you will have only this, and the equation will be like this. Okay? You see this part is gone. You have only the area, pile section, the pile tip area multiplied by Q prime, the NQ star. Okay? This equation is the one we have for sand. So the tip or end bearing capacity of pile in uniform sand, homogeneous sand, is given by this equation. It's very important for you to remember that. Okay. Now, in this equation, what do we have and what is unknown? You can see that AP is the area of the pile tip, so we can get that easily. Q prime is just the effective stress. So if you have the unit weight of the ground, you can get that also easily. And this one is the bearing capacity factor. That's the unknown. It's only this one that we don't have. So how do we